Math 1314, section IC1, spring 2022, Tyler Junior College, section 6.4, combinations and compositions of functions. Video 1, domains of functions. In this video, we're going to talk about the concept of taking two or more functions and combining them to make a new function. One of those ways to combine them is called composition. Excuse me. But before we have that discussion, we need to talk about something called the domain of a function. Now, we've heard the word domain before, and I want to remind you how that went. In order to define a domain, we first had to define a relation, and a relation was a set of ordered pairs. And within that relation, the domain was the set of first coordinates in a relation, and the range was the set of second coordinates in a relation. So when we first started talking about functions and we had something like this relation, in this case, the set containing the ordered pairs 1, 4, 2, 7, 3, 10, and 4, 10, then asking the domain and range was pretty easy. All we had to do was say the domain was the set of first coordinates, or x's, if you will. And in these four ordered pairs, the x's are 1, 2, 3, and 4. And the range was the set of second coordinates, which are 4, 7, 10, and 10. When we write a set, we don't repeat values, so we only write the 10 once. So the concept of domain and range was pretty simple back then. In most cases, we just had to look for the x's, look for the y's. But for a given function f of x, the domain and range are defined a little more specifically. Suppose f of x is defined by some formula. So for example, we might have something like f of x equals x plus 1 over x minus 2. So that's what I mean when I say suppose a function is defined by some formula. The domain of f of x, so we're defining that. Let's highlight it. The domain of f of x is the set of all real numbers x such that f of x is both defined and real. I want to emphasize those two words. Now let's think about this in terms of having a specific function. I guess I should have kept the one I had earlier. I don't remember what it was, but I think it might have been x plus 1 over x minus 2. When you have a given function written in function notation, then the domain is the set of everything that you can put into that function without causing problems. There's one number that can't go into this function. I want you to think about what it is. And we're going to focus on the words defined and real in just a moment. Now, the range of a function in function notation is the set of all real numbers y such that y is equal to f of x for some x in the domain. So in other words, the range is every possible output of a function based on knowing all the possible inputs. So when you're given a function notation and asked about its domain and range, it's not like this where I say, here's a few ordered pairs, pluck out the x's, pluck out the y's. When you're given a function in function notation, the domain is every possible number that can go in without causing problems. So it makes the function both defined and real. We're going to elaborate on that in just a moment. And the range is a set of all possible outputs based on putting in every possible input. Now, in this chapter, we will focus only on the domain of a function. There are three types of domain issues we will encounter. So let's start with the first one. The domain of a rational function. Now, a rational function, f of x, is a function of the form f of x equals p of x over q of x. Now, because I typed this, I couldn't type the fraction vertically. I had to type it horizontally. But if I were writing it, it would look like this. And there's some stipulations on p of x and q of x. P of x and q of x are polynomials, or polynomial functions, if you will. That just means there's sums and differences of powers of x, of whole number powers of x's. Because a rational function has a denominator, and because let's do this. Oops, I meant to make that yellow. I don't like just reading to you, but I know for some people it helps, but I'm going to have this little box floating around where I'm reading. Because a rational function has a denominator, and because a fraction is undefined when its denominator is 0, the domain of a rational function is the set of all real numbers such that q of x is not equal to 0. That's the denominator. This is because the domain of f of x is the set of all real numbers x such that f of x is both defined and real. So let's break this down. You have a function that's a fraction. Denominator can't be 0. So your domain is everything that makes the denominator not 0. So the key thing you need to focus on here is denominator, that's supposed to be a box, is denominator not equal to 0. This is actually pretty easy to do, because if the denominator was 0, that would make the function undefined, and the domain needs the output to be defined. So we're focusing on the number defined here. What makes a number undefined, at least at this stage, is if it's a fraction whose denominator is 0. So we have to avoid that. So let's take a look at a few examples. Find the domain of the following functions. The first one is f of x equals x minus 5 over x minus 3. So this one right here. Well, if we're going to find the domain, we need all numbers that make it both defined and real. We'll talk about the real part in the next type of function. Right now, we're focusing on what makes this function here defined. And it's kind of ironic because we focus on what makes it defined by focusing on what makes it undefined, excuse me. So in order to find that, the first thing we have to do one second, folks. First, we have to solve. I probably could have typed this. X minus 3 is equal to 0. Now, I know I just got finished saying that the denominator can't be 0. But if I know what numbers, if I want to know what numbers I need to avoid, I need to find the numbers that cause problems. In this case, any number that makes the bottom equal to 0 will cause a problem. Well, this is easy to solve. We just add 3 to both sides and we get x equals to 3. I'm going to switch over to typing here so that I can make sure it all fits in the space and it's legible. So first we solve x minus 3 is equal to 0 and we get x equals 3. This is the number we don't want in the domain. Let me take the font size down a notch so it'll fit a little bit better. This is the number we don't want because it's the number that makes the denominator equal to 0. So how can we describe what the domain is? In other words, how can we describe, we want everything except 3. Well, there's a couple of ways to say it. We can say the domain is the set of all x's such that x is not equal to 3. We could use set builder notation. However, the homework and future problems will want this answer in interval notation. So how would we write this in interval notation? Well, let's think about it for a second by thinking about a number line. If I drew a number line and put 3 in the middle, because that's the number I'm focusing on, then I can visually represent my domain by shading in everything except the 3. So how would I do that? Well, I could go right up to the 3 and stop, but how could I indicate at the 3 that I don't want to include it? Well, there's a couple of ways to do it. One way is to put an open circle on it. I just shaded everything except the number 3. Now, if you're wondering why didn't I use an open parentheses on both sides, I could have. In fact, I'm about to use parentheses because you're going to be asked for these domains in interval notation. Remember that an interval is a description of what's shaded on a number line from left to right. Parentheses if you don't include a number, bracket if you do, and infinities always get parentheses. From left to right, I shaded from open parentheses, negative infinity, comma 3, but then I have to use a closed parentheses on the 3 because I am excluding it from my domain. And I also have an interval on the right side of 3 that starts with open parentheses, 3, comma, goes all the way to positive infinity, close parentheses. But if I have an interval that has 2 parts, then I have to join them with a union. So the domain of this function is everything from -3 to 3 and everything, I'm sorry, -infinity to 3 and everything from 3 to infinity. So basically everything except 3. All right, let's take a look at the second example. I'm going to draw a line separating these two. There we go. All right, g of x equals 2x minus 6 over x squared plus 3x minus 10. Well, we're playing the same game. We want to find the domain of this function, so we have to figure out what makes it real and defined. And because it's a fraction, we're going to focus on what makes it undefined. And we focus on that by asking ourselves what makes the denominator equal to 0. So we need to solve x squared plus 3x minus 10 is equal to 0 so that we can locate the numbers that we want to exclude from the domain. I'm going to go ahead and draw a line separating the second and third examples, maybe, because I can tell I'm going to run over into the next problem's territory if I'm not careful. All right, so we have to solve this quadratic equation, and it's been a while since we've talked about quadratic equations. You can use the quadratic formula, or you can use factoring. One technique for solving is factoring, and this guy will actually factor. X squared plus 3x minus 10 will factor into x plus 5 and x minus 2. If you forgot why, go back and rewatch some of the videos about factoring trinomials. And if we're solving a quadratic equation that's factored on one side and 0 on the other, then we can set each factor equal to 0. So we have x plus 5 is equal to 0, and we have x minus 2 is equal to 0. Both of these are easy to solve. We get x equals -5, and we get x equals +2. But be careful. This is not the domain. These are the numbers that we want to exclude, because these are the numbers that make the bottom equal to 0. So keep in mind, we want what makes the bottom non-zero, but we find it by first finding what makes the bottom equal to 0. Since x equals -5 and x equals 2 makes the denominator equal to 0, that means our domain would be everything except those two numbers. Now, it's not necessary to draw the number line, but if it helps you write the domain in interval notation, you should do it. I drew a number line with -5 and 2. -5 being less than 2 is to the left of 2. And now I'm going to shade in everything except those two numbers. So from -infinity to -5, from -5 to 2, and from 2 to infinity. Notice I did not shade in -5 and 2 because I'm going to draw an empty circle on them. And so my interval notation for the domain will have 3 intervals. The left interval is open parentheses, -infinity, comma, -5, close parentheses, union, the middle interval, open parentheses, -5, comma, 2, close parentheses, union, the third interval, open parentheses, 2, comma, infinity, close parentheses. So again, our domain is everything except the values that make the denominator equal to 0. So we find out what makes the denominator equal to 0. And then our domain is everything except those numbers. All right, let's take a look at this last one before we move on to the next domain issue. H of x equals 5 over x squared plus 4. Well, it's a rational function, one polynomial over another. And yes, a number like 5 by itself is considered to be a polynomial. And so we're going to find the domain by solving the denominator equal to 0. So let's set x squared plus 4 is equal to 0. This is a quadratic equation, but it only has a single x term, so we can solve it using square roots. Subtract 4 from both sides to get x squared equals -4, and take the plus minus square root of both sides. We get x equals plus or minus the square root of -4, but the square root of -4 is 2i. So what does this mean for the domain? Well, by definition, the domain is the set of all real numbers that make the function both defined and real. The only numbers that make this function undefined are these. In other words, those two numbers would cause this denominator to become 0. But our domain, by definition, starts out as the set of all real numbers. And then we throw out the ones that make the denominator equal to 0. The numbers that make the denominator equal to 0 aren't even real. So, or think of it this way. If we try to do the same thing we did in the previous one, we would draw a number line, but where would you locate 2i and negative 2i on them? And the answer is you wouldn't. The real number line does not contain imaginary numbers. So there's nothing I would remove from the number line because the only numbers that are bad don't even live there. I guess in words, I could say something like this. If the only values that make the denominator 0 equals 0 are not real, these aren't, then the domain is all real numbers. Because, again, by definition, the domain starts out with the set of all real numbers that make the function real and defined. If the only numbers that make it undefined aren't real, then we don't have to worry about those. So our domain is all real numbers. And as an interval, we could say open parentheses, negative infinity, comma infinity. So just because there's a denominator does not mean there will be exclusions to your domain. If there is a denominator, you exclude any real number that makes the denominator equal to 0. If no real numbers make the denominator equal to 0, then the domain is everything, negative infinity to infinity. All right, let's take a look at the second type of domain issue, the domain of a square root function. Bring back the highlight box. I'm not sure if I like that or not. I'm going to try it again. And I'll just move it as I'm reading. Previously, we learned that the square root of a negative number is not real. Specifically, it is imaginary. However, the domain of a function f of x is the set of all real numbers, emphasis on the word real, x, such that f of x is both defined and real, emphasis on that real. So the domain of a square root function must exclude any values that make the radicand negative, the part under the square root. Translation. If we have a square root function, like f of x equals the square root of x minus 4, I can put in any number as long as it does not make the radicand negative. So for example, in this problem, I could put in 5 because 5 minus 4 is positive 1, but I couldn't put in 3 because 3 minus 4 is negative 1. Why? Because we're looking for values that make the function both defined and real. F of x is, let's shrink this down a little bit, is real. And with the presence of a square root, it is possible that there's a value that makes the function not real because we square root negative numbers, and we need to avoid those. Hence, and I'm reading the last sentence now, to find the domain of a square root function, we solve the inequality radicand is greater than or equal to 0. I think that is worth putting in a box. And I don't think I had something similar to that over here. I did not. One second. Okay, I fixed it. You'll see it at the very end. All right, so to find the domain of a square root function, we solve the inequality radicand greater than or equal to 0. So let's take a look at a couple of examples. Find the domain of the following functions. First one is f of x equals the square root of 2x plus, that's supposed to be a 10. It kind of looked like a 16, although I could have solved either one of them. All right, so starting with this function, because this is a square root function, we have to solve the radicand is greater than or equal to 0. So 2x plus 10 is greater than or equal to 0. What this does is guarantee that we will not end up square rooting a negative number, since we're forcing the part under the square root to be non-negative, greater than or equal to 0. Well, this is pretty easy to solve. We subtract 10 from both sides. Excuse me, to get 2x is greater than or equal to negative 10. Then we divide both sides by 2 to get x is greater than or equal to negative 5. We haven't solved inequalities in a while, but they still work the same way as before. If we wanted to draw the number line for x is greater than or equal to negative 5, we would locate negative 5. Greater than is to the right of it, so we would shade to the right of negative 5. But this includes negative 5. So if we were to put a circle, we would put a circle and then fill it in, or equivalently, we could put a bracket. And again, we're including the negative 5 because the inequality is greater than or equal to. That's because it's okay for the radicand to equal 0. So what's the interval for this number line? Well, from left to right, bracket negative 5 because it includes the negative 5, comma infinity. So that wasn't too bad. We just hadn't solved inequalities in a while. What about the second one? G of x equals the square root of 5 minus x. Well, pretty much the same song and dance. We need to solve 5 minus x is greater than or equal to 0. Now this one you should be a little more careful because even though it's a subtraction problem, the minus is in front of the x, and so that means you just proceed with caution. To get rid of the 5 in front, I'm going to subtract 5 from both sides. I know this is a subtraction problem and the opposite of subtracting is adding, but the 5 is positive and we need to counteract it with a negative 5. That would leave a negative x on the left, greater than or equal to 0 minus 5 is negative 5 on the right. And now to get the x by itself, we treat the negative in front like it's a negative 1x and then divide both sides by negative 1. Warning! This is one of the two moves that causes the inequality sign to turn around. When you multiply both sides of an inequality by a negative or divide both sides of an inequality by a negative, the sign reverses. So instead of greater than or equal to, it will now say less than or equal to. And on the right side, negative 5 divided by negative 1 is positive 5. This kind of makes sense because if you look at the radicand, I'm starting with 5 and I'm taking something away from it. And I want the result to not be negative, which means I can't take away anything bigger than 5. So I can take away anything 5 or less. As a number line, this is pretty easy. Here's 5. We would shade to the left since it says less than. And again, we would include the 5 because the inequality says x is less than or equal to 5. And so as an interval from left to right, it would be open parentheses, negative infinity, comma 5, bracket on the 5 because it's shaded in on the number line. So square root functions aren't too bad. There are some trickier variations that we don't get to, but in general, you just solve radicand greater than or equal to 0. The third type of domain issue is actually a non-issue, the domain of a polynomial function. Get my highlight going here. I don't know if this helps or not. It's just, there's so many words, it's easy to get lost if you're just listening. Since a polynomial function f of x has no denominators, no value of x will ever make f of x undefined. Remember, it's denominators being 0 that cause it to be undefined. No denominators, not a problem. And also, since a polynomial function f of x has no square roots, it only has x's raised to whole number powers, no value of x will ever make f of x non-real. So we're not square rooting anything, so we don't have any issues there either. Hence, every real value of x belongs to the domain of f of x. The domain of any polynomial function is all real numbers, or in interval notation, negative infinity to infinity. That belongs in a red box. All this is saying is that if you don't have any denominators and you don't have any square roots and you don't have any issues, your domain is everything, all real numbers. So for example, if I asked you to find the domain of the following functions, it's over. These are all polynomials. This one's a polynomial. It's powers of x's, whole number powers of x's, added and subtracted. And because of that, the domain is just everything. Negative infinity to infinity. I can put any number in this function without a problem. Sure, some answers will be large, some will be small, some might be inconvenient like fractions, but every number can go in and produce a real output. So the domain is negative infinity to infinity. And it's the same thing with this other one. G of x equals 1/200th, 1 over 200 times x to the 50th minus 11.7 times x to the 41st plus 1971. This is just a polynomial function. You can have decimals in the coefficients in front. You can have fractions in the coefficients, but as long as the exponents are whole numbers, 50, 41, then you are a polynomial function. And as a polynomial function, that means that your domain is negative infinity, comma infinity. Remember, our domain issues are invoked by denominators and square roots. And if you have neither, or rather I should say no variables in denominators, then your domain has no restrictions. It's everything, negative infinity to infinity. All right, so although there are only two types of functions with domain issues so far, it is possible to have a function with multiple domain issues. The domain of such a function must adhere to the domain requirements for each of these issues. Specifically, we have to avoid a denominator equal to 0, and we have to avoid negative radicands. When a function has multiple domain issues, start with the radicand first if there is one, then address denominators. For example, consider the function f of x equals the square root of x plus 2 all over x minus 1. This has both a square root and a denominator, and so the domain is going to be affected by both. Let's start with the square root. Because of the square root, we need the radicand x plus 2 to be greater than or equal to 0. Well, that's pretty easy to solve. We get x is greater than or equal to negative 2. So if we were to draw a number line, we would start at negative 2, include the negative 2, and shade to the right since it says greater than or equal to. But here's the problem with saying that's our domain. We have a denominator, and the denominator brings another issue. For the denominator, we need x minus 1 to not equal 0. Well, if we add 1 to both sides, that means x cannot be 1. Well, look at the blue number line that I shaded. It went right through the number 1 and includes it. So I have to adjust this domain to reflect the denominator's issue. I cannot include positive 1 in this domain. So how do we do that? Well, it's actually pretty simple. First, let's go locate the number 1 over here. And let me erase the blue shading in because it is currently shading in something we don't need. To exclude the 1, I can just put an empty circle around it. And now I can shade in according to the inequality x is greater than or equal to negative 2. Shade to the right of negative 2, but stop when I get to the 1, and then continue beyond there. So really, it's just the same shading I had before, but I removed where the number 1 is. And as a consequence, my domain is going to be bracket negative 2, comma 1, open parentheses, union, open parentheses 1, comma infinity. That's the interval notation for everything greater than or equal to negative 2 except the number 1. And my domain does accommodate each domain issue. It accommodates the square root greater than or equal to negative 2, but it also accommodates the denominator. X can't be 1. We're going to take a look at a few more multiple issues and then we'll wrap this up. For example, g of x equals 5x over the square root of x minus 4. There's something I forgot to mention when we talked about fractions. It doesn't matter what's in the numerator. The numerator can be anything. It's only the denominator that has a domain issue. So when we're finding the domain of a rational function, we normally don't focus on the numerator unless it has another issue like this one that had the square root in the numerator. All right, we have 5x over the square root of x minus 4, which means we have two domain issues. Domain issue number 1, we need x minus 4 to be greater than or equal to 0 because we don't want a negative number under the square root. Well, that's just x is greater than or equal to 4, and that's pretty easy to shade in. We'll figure that out in a minute. But we also need the denominator to not equal 0. We need the square root of x minus 4 to not equal 0. Well, we've solved square root equations before. All we had to do is square both sides. And you may be wondering, can we do all this with not equal to in the middle? Well, yes, you can. Or you can throw away the not equal to, solve that, and remember, this is the number we want to get rid of. We square both sides, it cancels the square root. We get x minus 4 is not equal to 0 squared is 0. And then add 4 to both sides, we get x cannot equal 4. So we need a domain that accommodates both of these requirements. X is greater than or equal to 4, but not equal to 4. Well, if we were to try to draw the number line, it would go something like this. Greater than or equal to 4 would look like this. Here's 4. We'll shade in at 4 because of the greater than or equal to. And then we'll shade in to the right because it says greater than. And that's the domain that we get from the red stuff, x is greater than or equal to 4. But now I have to remember that this means x is not equal to 4. So I have to remove 4 from this picture. Now 4 is the point where we shaded in. So how would I remove it? Well, I would unshade it and then put another circle that's empty. So we removed a point, it just happened to be the end point of the interval, unlike this one, where we removed a point in the middle. This interval is open parentheses 4 comma infinity, which accommodates both domain issues. Couple more. F of x equals 2 over x plus 1 over x plus 2. This has multiple issues, but they're multiple fraction issues. So we'll just address each one of them accordingly. We need x plus 1 to not equal 0, which means we need x to not equal -1. And here we need x plus 2 is not equal to 0, which means x cannot be equal to -2. So we simply need a number line that's everything except those numbers. Well, we've already seen a situation like this before. Here's -2, here's -1. Make sure you put them in the correct order. Our number line has to exclude those, so we'll put an open circle around them, but it includes everything else. So it includes the part to the left of -2, the part between -2 and -1, and the part to the right of -1. Making our interval, our domain in interval notation, open parentheses negative infinity, comma -2, close parentheses, union, open parentheses -2, comma -1, close parentheses, union, open parentheses -1, comma infinity. So everything except those two numbers. So that wasn't too bad. This isn't the only time we've seen two numbers excluded from a domain. I know it's here somewhere. The example in the middle also had two numbers excluded from the domain. Okay. Ooh, this one's scary, but manageable. This also has two denominators, but notice that there's a fraction inside of the denominator. Well, since we have two fractions, we have the big fraction here, and we have the little fraction here. We need to address both of those fractions' denominator issues. Let's start with the little fraction. Because the little fraction has an x in the denominator, we need the denominator to not equal 0. All right, well, there's nothing to solve there. It already has x by itself. So we can't let x equal 0 because of that fraction's denominator. But there was also this larger fraction with a larger denominator. The denominator of the large fraction is x minus 4 over x, and we need that to not equal 0. So how are we going to solve that? Well, we've solved rational equations before, and the strategy was to multiply to knock out the denominators. If we multiply both sides of this by x, because that's the only denominator in here, we multiply both sides of the equation by x, we can distribute on the left to get x squared minus, and then when we distribute the x to the 4 over x, the x's cancel, leaving a 4. And on the right side, we get 0 times x is 0. Great, a quadratic equation, but this one's easy to solve because it only has a single x term. You could solve it by factoring, or you could just add 4 to both sides and say x squared cannot equal 4, and then take the plus minus square root of both sides. And this implies that x cannot equal plus or minus 2. So it ends up there are 3 numbers I have to exclude from this domain. 0 because of the little fraction, and both 2 and negative 2 because of the big fraction. What would this look like? Well, it's pretty easy. Number line, we have to remove both 0, all of 0, 2, and negative 2. So let's locate all of those. We want those excluded from our number line, or our domain, so we'll put an open circle on each one of them. But those are the only numbers we want excluded, which means now we shade in everything else. To the left of negative 2, between negative 2 and 0, between 0 and 2, and from 2 to infinity. Our domain is open parentheses, negative infinity, comma, negative 2, close parentheses, that's the first part of the domain, union, open parentheses, negative 2, comma, 0, that's the second part of the domain, union, open parentheses, 0, comma, 2, close parentheses, that's the third part of the domain, union, open parentheses, 2, comma, infinity. That's the fourth and final part of the domain. Now, I'll be honest with you, I didn't give you one that crazy on your homework, nor will I give you one on your test. But it does show you that it doesn't matter how complicated a function is. There's really only 2 places to look at this point for domain issues. Any denominator can't be 0. Any radicand can't be negative, so we force it to be non-negative by forcing it to be greater than or equal to 0. All right, let's wrap up. Define the domain of a rational function. Solve the denominator equal to 0. And the domain is all real numbers except those solutions. The thing in the red box is how to set the problem off. Define the domain of a square root function. You simply solve radicand greater than or equal to 0. The domain of any polynomial function is just all real numbers, negative infinity to infinity. And if you have multiple domain issues, that domain must account for all such issues. My recommendation is to account for the square root first if there is one, and then use any denominators to remove values from the domain. All right, so that was a lot to do, but I needed to get the domain discussion out of the way before we started talking about combining functions.